Okay, so first of all, our discussion on abitic acid, right? Abitic acid is one of the important terpenoid. Abitic acid is one of the important terpenoid, right? And if I talk about abitic acid, then this is general formula of abitic acid, right? This is general formula of abitic acid. C20H30O2. C20H30O2. This is general formula of abitic acid, right? Now you can see what about structure of abitic acid. So this is about the structure of abitic acid. You can see, right? This is the structure of abitic acid, right? So here you can see 1 ring, 2 and 3 ring. It means it is tricyclic compound. It means it is tricyclic compound. We had already discussed the number of carbon are 20 and the number of hydrogen are 30 and the number of oxygen are 2. You can see here 2, right? So this is structure. You can see tricyclic structure, 1 cycle, then 2nd cycle, then 3rd cycle, right? What is the other important point in abitic acid? Because it is acid, so you can see here COOH, right? You can see here COH. This is reason why it is acid and why we call that abitic acid. This is reason, right? COH. Now, what about the other important point in their structure? You can see here it is angular methyl group. This is one of the important substituted group, right? Angular methyl group. Then you can see this is also one of the important methyl group, right? COH, we people already know, carboxylic acid group. Now, next here you can see here conjugated double bond. You can see this double bond and this double bond, they are conjugated, right? So conjugated double bond also important point in abitic acid structure, right? And last one you can see meth, eth and prop, right? So propyl group, it is side chain isopropyl group, right? So this is basic structure of your abitic acid. This is basic structure of your abitic acid, right? Where 3 rings, so it is called tricyclic compound. So it is called tricyclic compound, right? Second important thing is here COH group. It means it is a carboxylic acid or it is a acid, right? Now, next important point, you can see this is angular methyl group at carbon 10, right? At carbon 10, you can see here angular methyl group, right? And other one at first position, other methyl group at first position. Next, if we talk about side chain, you can see isopropyl group. One of the important side chain is isopropyl group, right? And last, very important group, you can see it is conjugated double bond, right? So this is overall structure of abitic acid. This is overall structure of abitic acid. Now the point come, how do we determine the structure of abitic acid, right? So for that we need to go one by one, right? We need to do some chemical reactions for determination of structure of abitic acid. Either there is carboxylic acid or not. It will confirm by some chemical test. It will confirm by some chemical test, right? After that, next point, either their conjugated double bond or not, it will also confirm by some chemical test. Either their isopropyl group or not, it will confirm by some test, right? Angular methyl group, it also confirm. It is tricyclic compound, it also confirm. At first position methyl group, it also confirm, right? So those chemical test or chemical reaction come under their chemical examination or structural determination, right? Now you can see one by one. Now you can see here one by one, right? Here, first of all, very important group, that is carboxylic acid. So either in abitic acid COH group present or not, it confirmed by few reactions. So you can see mostly, when we use sodium bicarbonate, actually it is Na, right? Sodium bicarbonate, right? So when we add a small amount of sodium bicarbonate in abitic acid, then effervescence of carbon dioxide will release, right? And when effervescence of carbon dioxide gas release from abitic acid, so it confirms there is COH group, right? Then how do we confirm the presence of COH group? It is when we take a small amount of abitic acid in a test tube and then we add, right, a small amount of sodium bicarbonate. After that, if the effervescence of carbon dioxide release, we confirm there is COH group, right? After that, next point come the carboxylic acid. Carboxylic acid present at primary, secondary or tertiary carbon atom, right? So here, carboxylic acid present at tertiary carbon. Why? You can see here, right? This carbon, here CH, here CH2, here CH3. It means this is tertiary carbon. This carboxylic group attach at tertiary carbon. And if that attach at primary or secondary, then the reaction is easy. But because that exists at tertiary carbon, so difficulty in their esterification. It's not possible for us. We can easily esterify our COH group, right? So difficulty in esterification confirm your carboxylic group attach at tertiary carbon, right? So it confirmed by esterification test. What about esterification test, right? You have a carboxylic acid already in abitic acid. When they react with alcohol, right? When they react with alcohol, then fruity smell come out, right? And that is esterification test. You people already know, right? So difficulty in esterification confirm the carboxylic acid attach at tertiary carbon, right? It should be clear. Now after that, next point, right? Abitic acid, when we add few drops of concentrate sulfuric acid in abitic acid, right? So then not easily carbon monoxide evolved, but when we heat that, then carbon monoxide evolved. By that we confirm our carboxylic group attach at tertiary carbon. Our carboxylic group attach at tertiary carbon, right? So it should be clear. Either their COH group and at which carbon that COH group exists, either primary, secondary or tertiary, right? So now it is confirmed by these reactions. Now after that, next point come, how many double bond exist in your carboxylic, in your abitic acid, right? So it is, very simple, right? How many double bond exist, right? So, unsaturated compound convert into saturated compound, addition reaction, right? Hydrogenation is one of the important addition reaction, right? So either compound is unsaturated or not, it confirmed by addition reaction or it confirmed by hydrogenation reaction, right? So in presence of nickel, you people already know, right? Nickel is a very good reducing agent, right? In presence of nickel or rainy nickel, in presence of rainy nickel or nickel, when abitic acid react with two molecules of hydrogen, then they convert into tetrahydroabitic acid, which confirm there are two double bond here. That confirm there are two double bond, right? So in abitic acid, two double bond exist. It is confirmed by this reaction, by reduction reaction or by hydrogenation reaction in presence of nickel, because C19H29COH, right, when react with two molecule of H2, right, they convert into C19H33, right? It means 4 hydrogen add. Why 4 hydrogen add? Because of two double bond, because of two double bond, and the final compound is tetrahydroabitic acid, right? The presence of two double bond confirmed by this reaction, right? Now next, after that, next important point, as I already told, the compound is a tricyclic nature. The compound is a tricyclic in their nature. How do we confirm the compound is tricyclic in their nature, right? So general formula, you know about the general formula, right? So now what about the general formula of tricyclic compound? The tricyclic compound general formula is CnH2n minus 4. But before that, But before that, you know, there are two double bonds. So first we need to reduce. First we need to reduce our abitic acid into this compound C19H33 and COH replaced by hydrogen, right? Then they convert into C19H34. Then they convert into C19H34, right? So after complete reduction of abitic acid, first they convert into C19H33COH. After that, if we do their further reduction, so then CO2 will remove out and they convert into C19H34. C19H34. And now, you know, C19H34, it means CnH2n minus 4, because 19, when you multiply that by 2, right? When you multiply that by 2, then they convert into 38, right? Because here 34, so 38 minus 4 equal to 38 minus 4 equal to 34, right? So in this way, C19H34 is general formula of tricyclic compound. The general formula of tricyclic compound. So either compound is tricyclic or not, it will confirm by hydration saturation test. It means first we need to convert that compound into saturated compound. It means two double bond convert into single bond. It is by addition of 4 hydrogen, and after that COH group removed by hydrogen and they convert into C19H34, right? Which belong to the formula of CnH2n minus 4, right? And that is general formula of tricyclic compound, right? So it is about confirmation of tricyclic nature of abitic acid. Now after the next point come methyl group present at position first. You know, two methyl group, one is angular methyl group and second is the methyl group at first position. So how do we confirm methyl group present at first position, right? So abitic acid have 20 carbon atom. You people already know in abitic acid 20 carbon atom, you know, C19 plus 1 carbon with COH. It means the number of carbon are 20, right? So in presence of sulfur or selenium, right, or lead or charcoal, right, dehydrogenation. After dehydrogenation, your abitic acid convert into rentin, right? Or that convert into 1 methyl 7 isopropyl phenanthrene. That convert into 1 methyl 7 isopropyl phenanthrene, right? You can see. So because at first position methyl group, so it confirm the position of methyl at first position, right? So methyl at first position clear with help of this reaction, right? So when your abitic acid, right, by dehydrogenation, right, convert into C18H18, right, rentin, or 1 methyl 7 isopropyl phenanthrene, right? So that confirm because at first position methyl, so you can say methyl group exists at first position by this reaction, right? Now after that you can see position of carboxylic group, right? Now the point come, what about the position of carboxylic group, right, or first position of carboxylic group? For that we need to do some more reactions. Right? So the position of carboxylic, first point is either there is carboxylic acid or not. First point is either there is carboxylic acid or not. And after that, what about second point? The second point is, The second point is, you can see here, second point is, what about the position? So two things are important. One is either carboxylic acid exists or not. One thing is either carboxylic acid exists or not. And second thing is, what about the position of carboxylic acid? Right? So two things are important. Either functional group exists or not. And second, if functional group exists, then at which position. So now same point come, now same point come, you can see here, now the same point come, you can see here same point come. So carboxylic acid exists at first position, right? So how do we clear that? So first we need to do their reaction with alcohol in presence of HCl, right? Alcohol in presence of HCl, right? Then they convert into methyl abitic, right? It means they convert into ester, right? Carboxylic acid react with alcohol, it means they convert into ester, right? So you can see, and that reaction takes place in presence of HCl. It means the reaction takes place in presence of strong, it means the reaction takes place in presence of strong acid, right? In presence of strong acid. Now after that you can see, right? Very important thing. Now after that you can see how that react with sodium and C2H5OH. It means reduction with sodium metal and ethanol, reduction with sodium metal and ethanol, right? So when reduction with sodium metal and ethanol, when reduction with sodium metal and ethanol, then they convert into, you know, sodium and ethanol is a good reducing agent, then they convert into alcohol. You can see they convert into alcohol abitinol, you can see they convert into alcohol abitinol. First here COCH3, and then after reduction they convert into abitinol, right? So it means you can see here, right? They convert into CH2OH, abitinol, right? And after that, if they react with PCl5, phosphorus pentachloride, then H2O will remove out. And then this CH3 come at this position. When H2O will remove out, H2O, then here CH and here CH3. So they convert into CH2CH3, C2H5, right? They convert into C2H5, right? And this is called ethyl abitine. That is called ethyl abitine, right? They convert into ethyl abitine, right? Now you can see here CH double bond, right? CH2. So in this way they convert into ethyl abitine, right? And after that you can see if they react with S, then they convert into this types of compound which is called homorethane, right? C19H20. So because C2H5 at first position, we can say carboxylic acid exists at first position, but the reaction is not complete. This is a problem with natural product. Right? What is the problem with natural product? Actually the problem is you can see here, problem is the reactions are so long. So because the steps are much more, so the problem to learn or the problem to complete the reaction, right? And here this point come, right? You can see because the number of step increase, right? First step where abitic acid convert into after esterification convert into methyl abitate, right? And after reduction they convert into abitinol, right? You can see. Then after that they react with PCl5, water molecule remove out, they convert into ethyl abitine, right? After that react with sulfur and they convert into homorethyl, right? And here C2H5, right? And after that, next you can see rethyl or homorethyl. Either we talk about rethyl or homorethyl. Both when react with potassium ferricyanate, then they give same types of product, right? One is called, that product is called phenanthrene 1,7 dicarboxylic acid. So because at first position COH, so we can say carboxylic acid exists at first position, right? So phenanthrene 1,7 dicarboxylic acid that your COH group exists at first position, right? Because rutene and homorutene both give same types of product when they react with potassium ferricyanide, right? So this is the point, right? And homorutene, how do we produce homorutene? You can see this is homorutene, right? And rutene we have already discussed, right? Here this is rutene, right? You can see there, this is rutene, right? Abitic acid, when dehydrogenation, then C18H18, and that is rutene, right? And now you can see, right? That is rutene, and you can see homorutene, right? This is C19H20, homorutene, right? So either homorutene or rutene both give same product when they react with potassium ferricyanide, right? And that product is phenanthrene 1,7-dicarboxylic acid, right? So because here the position of COH group first, so we can say, right, our carboxylic acid exists at first position, right? And you know, second carboxylic acid for isopropyl group, right? So in this way, this is the important reaction by which you confirm the position of carboxylic acid, right? Maybe in your final exam question based on the position of carboxylic acid group or carboxylic group in abitic acid, then you need to give these reactions, right, one by one, right? Sometime the question based on complete structural determination of abitic acid, so then you need to give all these reaction one by one, right? So this is the point. Now after that you can see next point, position of angular methyl group. Now the next point is the position of angular methyl group, right? So now you know angular methyl group, sorry, angular methyl group missed from this position. Actually, you know, here angular methyl group, right, CH3 group, you can see we had already discussed this point when we discuss about the structure, right? So at 10 position, right, your angular methyl group, that means here, but you know the position of angular methyl group at 10th position, right? So here angular methyl group, so this is abitic acid, you can see, right? Now our discussion on position of angular methyl group. Now our discussion on position of angular methyl group. How do we confirm the position of angular methyl group at 10th position? So for that we need to give some reaction. You can see here abitic acid. Now you can see here abitic acid when oxidized by potassium permanganate, KMnO4. You know, potassium permanganate is a strong oxidizing agent that release nascent oxygen, right? So when abitic acid oxidized by potassium permanganate, right, then they convert into two isomers, or you can say two tricarboxylic acid, not isomer, two tricarboxylic acid, right? You can see what about the structure of these tricarboxylic acid. You can see COH, then COH, and then COH, right? You can see here angular methyl group as it is, right? After that second one, you can see COH, COH here and here, COH and here COH, right? Here angular methyl, right? So in structure 1 and in structure 2 you can see angular methyl, right? Because during this reaction, this cyclic compound, degradation of this cyclic compound, not a cyclic part or substituted group. So methyl group at the position of 10 and at the position of 1 as it is. Just this carbon oxidized into COH and this carbon oxidized into COH, or this carbon oxidized into COH, right? And then they finally convert into tricarboxylic acid. So compound 1 and compound 2 give information about presence of angular methyl group at 10th position, right? You can see tricarboxylic acid first, you can see this, right? Dehydrogenation of this tricarboxylic acid. So when dehydrogenation of this tricarboxylic acid in presence of Se, they convert into metaxylene. Then they convert into metaxylene. You can see benzene, here CH3 and here CH3, right? So they convert into metaxylene, right? So when tricarboxylic acid 1 after dehydrogenation convert into metaxylene, then you can see methyl group at this position and this position. Now it confirmed, because you people already know one methyl group already present at first position. So second methyl group, it means present at this position, and it is actually 10th position. It is metaxylene, but you know this is 10th position in case of abitic acid. So now the position 10th position of angular methyl group confirmed by the product metaxylene, right? So metaxylene, clear, your angular methyl group exists at 10th position. Not only this reaction, other reaction also, right? After that, after confirmed position of angular methyl group, next point come about the position of conjugated 2 double bond. 2 double bond is already confirmed by hydrogenation reaction or reduction reaction, because your compound when react with 2 molecule of hydrogen, your compound when react with 2 molecule of hydrogen, right, then they convert into saturated product. So the number of double bond is already confirmed. The number of double bond is already confirmed. Now the point come, either your 2 double bond in conjugated position or not, right? And what about their position? So it is clear by this reaction. When abitic acid react with malic acid above 100 degrees Celsius temperature, when abitic acid react with malic acid in presence at above 100 degrees Celsius, then they convert into adduct, and this type's adduct form, right, where one carbon attach at this position and second carbon attach at this position, right? So this types of adduct form where it is malic anhydride, right, one carbon attach at this position and second carbon attach at this position, this types of adduct form, right? Now second important thing, your abitic acid absorb 239 nm lambda max in UV visible region. It shows there is a conjugated double bond, because you know on the basis of lambda max in UV visible spectra, you can confirm either the double bond are conjugated or not. So UV spectroscopy also important technique for clear about your abitic acid is in your abitic acid conjugated double bond or not, right? So one thing, with help of UV spectroscopy you can confirm there is conjugated double bond, and second by some chemical reaction, right? And you know one of the important chemical reaction is when they react with malic anhydride. When they react with malic anhydride, to when they react with malic anhydride above 100 degrees Celsius temperature, right, above 100 degrees Celsius temperature, then they convert into this types of product. Then they convert into this types of product which confirm the position of conjugated double bond, which confirm the position of conjugated double bond, right? Now after that, next point, right, now after that you can see next compound after abitic acid, second terpenoid is carotene. Now what about carotene? Beta carotene. So beta carotene also very important terpenoid. After abitic acid, according to your syllabus, next terpenoid is beta carotene. Beta carotene also a very important terpenoid. It occur in all the green plants, right? It occur in all the green plants. It is isolated from carrot, right? So you know this is one of the important terpenoid exists in green plants, right? It is one of the important terpenoid exists in green plants, right? Now how do we isolate that, right? And what about their structure? How do we determine their structure, right? Now the point come one by one. So you can see this is a structure. Actually, this is a structure of beta carotene, right? You can see it is a very, very perfect symmetric structure. It is a very, very perfect symmetric structure, right? You can see here it is cyclohexene. You can see right here two methyl group, here two methyl group and one methyl group at this position, right? One double bond, then single bond, then double bond, then single bond, then double bond, single bond, double bond. So in this way, conjugated double bond. There are so many conjugated double bond, right? And you know, isoprene unit, you know, CH double bond CH, then C, then CH3, then CH. So in this way, it is isoprene unit, one isoprene unit, then CH, double bond CH, single bond C, CH3, double bond CH, second isoprene unit, third isoprene unit, fourth isoprene unit. 1, 2, 3, 4, four isoprene unit. You can see right here, four isoprene units are connected or joined, right, along with two hexacyclic ring, right? So this is complete structure of beta carotene. This is complete structure of beta carotene, which is one of the important terpenoid, which is one of the important terpenoid. Now after that, you can see what about the molecular formula, right? So from analytical data, it is confirmed the molecular formula of beta carotene is C40H56. What about their molecular formula? So C40H56 is their molecular formula. On the basis of analytical data, it is clear, right? And it is confirmed. Now after that, how many double bond? So there present 11 double bond. There present 11 double bond. How do we confirm that? You people already know, by hydrogenation reaction, right? So C40H56 when react with 11 molecules of hydrogen, when react with 11 molecules of hydrogen, then they convert into C40H78. It confirm 11 double bond exist in beta carotene. 11 double bond exist in beta carotene, right? So by simple addition reaction with hydrogen, you can confirm how many double bond exist in your beta carotene. And finally, they convert into per hydro beta carotene, right? So this is reaction by which we confirm 11 double bond exist in beta carotene. Now after that, the compound is bicyclic because there are two cycles, so it is bicyclic compound. How do we confirm that, right? C40H78, right? Complete saturated compound where all 11 double bond reduce, right? That compound C40H78 belong or correspond to general formula CnH2n-2. CnH2n-2. It means the compound is bicyclic in their nature, because we had already discussed in abitic acid, if the general formula is CnH2n-4, it means your compound is tricyclic compound. It means your compound is tricyclic. But here the general formula is CnH2n-2, so the compound is bicyclic in their nature, right? So either your compound is bicyclic or not, it is confirmed by their general formula, right? Now after that, presence of 5 conjugated double bond. There are 5 conjugated double bond. How do we confirm that? You know, in abitic acid, how do we confirm that? When they react with malic anhydride above 100 degrees Celsius, right? So when they react with malic anhydride, they absorb 5 mole of malic anhydride, because they absorb or they add with 5 mole of malic anhydride, and to form a crystalline adduct or crystalline product, right? So when they absorb 5 molecules of malic anhydride, by that we can say there are 5 conjugated double bond, or in beta carotene 5 conjugated double bonds, right? So this is also important point, how many conjugated double bond exist in malic anhydride. Now after that, you can see presence of 2 beta ions units, right? The beta carotene on oxidation convert into beta ions, right? So when you oxidize that with a strong oxidizing agent, then they convert into this types of compounds, right? They convert into these types of compound, right? And these compound very important for confirm the final structure of your beta carotene. So you can see, right? Beta carotene when react with ozone, you know, it is also a strong oxidizing agent, right? So they convert into these types of two compound like this, right? And further they convert into two compounds like this, right? So they convert into these types of compound, which clear about hexacyclic structure in beta carotene, right? Now you can see, if you think about your beta carotene, or if you think about structure of beta carotene, right? Then you can see this is one hexacyclic ring, and this is second hexacyclic ring, where two methyl group, and here one methyl group, two methyl group, one, and then you can see one single bond, then one double bond, then one single bond, then double bond, then one single bond. So in this way, C14 carbon between these two, 14 carbon between these two hexacyclic ring, right? So this is about basic structure, right? Now the next point comes presence of methyl side chain, right? I will discuss this point, right, in coming PPT, right? No problem, I will explain it once again, right? At the end of final structure, we will discuss these PPTs, right? How C14 and how many carbon exist between two hexacyclic rings, right? You can see other important point, presence of methyl side group. How do we confirm presence of methyl side group? So, you know, when we oxidize beta carotene, you can see when we oxidize beta carotene by ozone, they convert into this types of compound. They convert into this types of compound and this types of compound, right? This types of compound and this types of compound, and this compound is called gyronic acid. This compound is called gyronic acid, right? Here COH, here C double bond O and CS3. When we oxidize that compound with a strong oxidizing agent which easily release nascent oxygen, then one CH3COH will remove out. It means one carbon will remove out from this position, and then they convert into 2,2-dimethyl glutaric acid. This is 2,2-dimethyl glutaric acid, right? You can see COH as it is CH3, CH2, CH2, COH. It means one carbon remove out by oxidation in the form of CH3COH, and gyronic acid convert into 2,2-dimethyl glutaric acid. After that, once again, if we oxidize, right, with a strong oxidizing agent, other molecule of CH3COH